start the recording and go home for a second, see where we're at. We're still like a day and a half behind schedule, no big whoop. Just make sure the due dates are okay. So let's see. Limits at infinity I set to be due tonight. I think that's still reasonable. Applied optimization, I'm going to move that one. And I'm going to make your weekend here by setting it to Sunday night. And if you want to apply a late pass to give you another day, go for it. We will do more. And the reason I'm doing that is I just want to motivate you to actually start it before it's due. You should always start an assignment before the day it's due. Okay. So I'm going to put this to Sunday. If you want to apply a late pass, you may. And I just want to give you an example of a problem I'm very curious about, and I want to show it to you. Stop share, please. All right, so you should be able to see me now, right? So I brought with me today a can of coconut cream. I love coconut cream. So I put coconut cream in all kinds of things I bake instead of regular cream. I put it in my coffee. Yum. And this can, I don't know if you can see that at the bottom. Can you zoom in on that? Show in the right spot. I don't know if you can see that. It's got 400 milliliters of coconut cream in there. And then I was looking at the shape of the can, right? It has a certain height and a certain diameter or radius there. And I was wondering, does this can use the least amount of tin or aluminum, whatever metal it's made out of, probably a combination of something. Does it use the least amount of metal to contain 400 milliliters? That's what I want to know. And I think we can figure that out. So you guys are going to help me figure out if the dimensions of this can, and I have a ruler here, I can measure that. So let's see. Let's go on this side. It is a little over 11 centimeters tall, and the diameter is roughly 7.5 centimeters, or yeah. So it's roughly here over 11 and just a little bit under 7.5. All right, so let's try this. I'm excited about this problem. So what we are going to do is we're going to see if we can find a minimum surface area for a can. And a can is a cylinder, and a cylinder has a circular top and a circular bottom, and the sides of that come down at a right angle. So we come down at a right angle there, and the measurements I need to define this are the radius of it and the height of it. And my particular can,
hey, you're not screen sharing.
Oh shit! Thank you. Oh, I just recorded that. Screen share. So you just got to watch me talk. All right, let's try that again. All right, here we go. Minimum surface area for a can. So see my can? Not the best drawing, but we're going to go with it. Circular top, circular bottom, sides come down at a right angle, need a radius and a height. And my can, I think the height was about a little, let's see, what do I think it was? A little over 11. So maybe it's like 11.1 centimeters. And I thought the diameter was about, say, 7.4 centimeters. So that means the radius would be half of that. So half of 7 is 3.5, 6, 7, so that would be about 3.7 centimeters. And I'm wondering, do these dimensions use the least amount of metal to make the can? So things I know here, the surface area of a can like this, if you peel off the label around the outside here, you get a rectangle. So this would be like the label of the can. And the height of that label is the height of the can. And this length here was peeled off. That's the circumference. So that would be 2 pi r. And so if I multiply those two, that would give me the area of that label. So I've got 2 pi h as part of my surface area. And then I have the lid on the top and the lid on the bottom. So I have 2 circles at pi r squared. So this would be the surface area of my can there. Now, one problem with the surface area is a function of two variables, and we are used to using functions of one variable. So we have to deal with that. We somehow have to get one variable. And the catch here is that I know what I want the volume to be. I want the volume to be 400 milliliters. And milliliters is a beautiful measurement because 1 milliliter is a cubic centimeter. So that means I actually have something related to the height and the radius, 400 centimeters cubed. Okay, so that is important there. And volume of a can like this is just the area of the base times the height. So that would be area of the base is pi r squared times the height. So this is the volume of this cylinder. And I claim I want a volume of 400 cubic centimeters. And so that works out good because my R is measured in centimeters. So if I have centimeters squared from R for the area, H is measured in centimeters times centimeters. So my units are going to match up there. So anytime we do a problem like this with units, we got to make sure units work out in the end. What this is going to allow me to do is then solve, I have a system of two equations and two unknowns, right? One equation there, two variables, one equation here, two variables. Now, again, we have this function over here that's also a variable, but that's okay because we're going to take a derivative on that in a second, and that's going to help us out. And I'll explain why the derivative is useful. So let's see, the easiest thing to do here, I think I'll just solve for H. So H, in this case, would be equal to 400 over pi r squared. So important thing here, I'm minimizing the surface area of a can where I know the volume to be 400 cubic centimeters. And without that, I really can't fully solve this problem. So then what I'm going to do is back in the surface area, I'm just going to call that S for surface. I can now rewrite that by replacing the H with that right there. So I've got 2 pi r times 400 over pi r squared plus the 2 pi r squared. And we can clean that up a bit. So let's see, the pi's divide out, and one of these r's divides out. And then I have 2 times 400, which is 800 over r. Yep, that looks good. And oops, equals plus 2 pi r squared. So now I've been able to write S as a function of r. And we played earlier with maxima and minima. And so what I'm hoping is there is an r, a value of r, that leads to the smallest surface area. So that's what I want to do next. So based on this function of r, can we find a value for r such that S is a minimum? Well, that's what the derivative helps us find. So let's take a look at that. So we want to take the derivative of our surface area with respect to the radius. And our surface area function is the 800 over r plus, oops, 2 pi r squared. Make sure I wrote that right. Yep, looks good. So taking the derivative of this function with respect to the radius, a couple ways to think about that. Either you remember the derivative of a reciprocal, or you have to think of 1 over r as r to the negative 1. And so this is one I happen to have memorized, that the derivative with respect to r of 1 over r is equal to negative 1 over r squared. And you can double check by using the power rule on that right there if you wish. The 800 is just a multiple, it gets carried along. So I'm going to get negative 800 over r squared for the first part of this sum. Second part is just a straight power rule. 2 times 2 is 4. So I get 4 pi r for the derivative of that part right there. And what I want to know is, does this have any critical values? One way to find critical values is to set it equal to 0. Now, just looking at this function, r cannot be 0, right? And that's a good thing, because if I have no radius, I have no can. So just a point of information, r can't be 0. That could be a critical value if it was defined in the original function, but clearly it's not, and it's a can. So otherwise, solving this, I should find a common denominator. So to solve this here, I am going to have to view that as over 1. Common denominator would be r squared. So I'm going to have to multiply in an r squared, top and bottom. So my new function is negative 800 plus 4 pi r cubed all over r squared. And the only way this can equal 0 is if the numerator is 0. Denominator can't be 0. So that makes this a little easier to solve. So now I have negative 800 equals, oops, not equals, but plus 4 pi r cubed, and then equals 0. And we can add the 800 to the other side. Divide by the 4 pi. And before we take the cube root, let's clean that up a little bit. 4 goes into 8 2 times, so 800 would be 200 when I reduce that. And then I can take the cube root. So r would be the cube root of 200 over pi. So I do believe I have a value for the radius. We'll check that in a minute on the graph, but I'm looking for the dimensions of my can. So a couple things I want to do. I want to approximate that to figure out how many centimeters that is, and I also want to figure out what h is. Now remember, back here we have an expression for h, and that was the 400 over pi r squared. So let's clean that up and see what happens. So h equals 400 over pi r squared. And so dealing with that there, let's see, what do we get? It's going to get a little bit messy. I think I'm going to rewrite that as the 1/3 power. So 200 over pi to the power 1/3, because then it's easier to square. So now I have 400 over pi times 200 over pi in parentheses to the 1/3 squared, which would be 2/3. And I'll work on cleaning up that in a minute, but right now I just want to know what those are approximately to see if the can I have at all relates to this. Then we'll look at the graph to see if this does seem like a minimum point. Calculator time. And I don't think I need these other ones. Goodbye. 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 And new screen. And here we have to use a function of x instead. First, I just want to figure out what those numbers are. So the r was the cube root. So I think I'll use parentheses in the 1/3 power. I know there's a cube root there somewhere. 200 over pi to the power 1/3. Write that correctly. 200 over pi to the power 1/3. Yep. So that's going to give me about almost 4 centimeters. And let's see, what was my can? My can was 3.7. Hey, that's almost 4. Oops. Here, and then I'm going to plug in this messy other one. I'll try to clean that up in a minute. I bet that cleans up nice. Calculator, please. So the other one was 200, no. 400. Ooh, I didn't want you to do that, GeoGebra. Oh. All right. 400 over pi times that radius above squared. And oh, the GeoGebra called it a, so I can just say multiply by a squared. And that would be about 7.9, almost 8. So my can optimally should be a little bit wider and shorter. Mine's 11, this says about 8 should be the height. Interesting. And then look at the graph of this. So here I'm going to graph S of X. I have to use X. And I had 800 over X plus 2 pi X times X squared. Make sure I got that right. 800 over R plus 2 pi R squared, yeah. And then we just have to grab a window that makes sense in. So let me see. I never did calculate the surface area, and my radius should be somewhere between 0 and, yeah, so that's reasonable there. I just need to adjust the vertical scale, and we should find that there's a minimum point once we get into the right region. There it is. And so we think there's a minimum over here just before 4. So let's graph the line X equals this number right here, which I can just call A thanks to GeoGebra. And so that seems to be the minimum value. That looks reasonable on the graph there. And so the can manufacturer picked a slightly different one, which is fine. That is also on this curve. So if I measured those better, I would be able to find that point on the curve that the manufacturer used instead. And just real quick here, I want to try and clean up this value of H, because I think that will clean up. Let's see. New page. So I've got 400 over pi times 200 over pi to the power 2/3. And then we can break that up, distributing the 2/3 to those two things. So that's 400 over 200 to the 2/3. And then I have pi over pi to the 2/3. That cleans up pretty good. That's just going to be pi to the power 1 minus 2/3. 1 minus 2/3 is 1/3. Right. In the bottom, so I'm going to get a pi to the 1/3 down here, cube root of pi. And then let's see, can we clean up 400 over 200? Yeah, we could write 400 as 2 times 200. And then we'll have 200 over 200 to the 2/3. So same thing, 200 to the 1 minus 2/3 power gives me the cube root of 200. And then I have the times 2. So then I'm going to get 2 times 200 to the 1/3. So that is another way to write that. Oh, these are both to the 1/3, so that's 2 times the cube root of 200 over pi. And wait, cube root of 200 over pi looks familiar. Where did we see that? That's my radius. Interesting. So the optimal dimensions here are that the radius is equal to the cube root of 200 over pi. Oops. So I was just looking, is there some significance to the number we found for H? And we found that H is twice that radius, which is the diameter. Oh my gosh. The height is the diameter. So if we look at the cross section of our can, this is pretty cool. The cross section of the can is a perfect square that the height and the diameter of my can make a square right through the middle of it. Kind of cool, square cross section. Wow, the beauty of geometry. And a square is an optimal area for a given perimeter. Wow, that's mind-blowing. All right, so we're just scratching the surface on optimization problems. So Again, in some cases, it's too much different than the min-max problems we did earlier. We're just applying them to a situation. And the hard thing is finding the equations that are relevant in that situation in order to take the derivative down here. So thanks for playing with me today. It's good to see you all. And we will do some more math together on Monday. In the meantime, try some of these problems. Don't worry about getting them all done by Monday, but get some done. I put the due date to Sunday just to kick you in the pants to make sure you do some math. So do math. Ta-ta.